Hello everyone. Let me begin with a quick question. Have you ever opened up an electronic device and noticed a group of capacitors soldered together on a circuit board? Why not just use one big capacitor instead? Well, just like we combine resistors to achieve a desired resistance, we often need to combine capacitors to tailor the capacitance to suit a circuit's needs. There are two main ways we do this. One is by connecting capacitors in series and the other is in parallel. Each method changes the total capacitance in a different way. In fact, series combinations result in a lower total capacitance than any individual capacitor, kind of like resistors in parallel. On the other hand, parallel combinations give us a larger total capacitance, ideal when we need more charge storage at a given voltage. Take a camera flash, for instance. It needs a lot of energy stored quickly and discharged in an instant. That's where capacitor arrays come in handy. Let's now explore each combination in detail.
Let's start with series combinations. Imagine three capacitors connected end to end, like beads on a string. Here's the interesting part. The charge on each capacitor is the same, but the voltage across each can differ. This happens because the same charge has to pass through each. There's nowhere else for it to go. But since their capacitances vary, each one builds up a different voltage. Now let's derive the formula. We start with the total voltage V being the sum of voltages across each capacitor. V equals V1 plus V2 plus V3. Now, since V equals Q over C, each term becomes Q divided by C1 plus Q divided by C2 plus Q divided by C3. Factoring out Q, we get Q multiplied by open bracket 1 over C1 plus 1 over C2 plus 1 over C3 close bracket. This tells us 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3. So the total or equivalent capacitance in series is less than the smallest individual capacitor. As shown in the diagram, while the capacitors share the same charge, the voltage is split across them. This setup is useful when you want to operate capacitors at voltages lower than the supply, like in high voltage circuits.
Now let's talk about parallel combinations. Here, all the left terminals are joined together and all the right terminals are joined together. So, the potential difference across each capacitor is the same. But the charge stored is different depending on each capacitor's value. Let's work through the derivation. The total charge stored is Q total equals Q plus Q plus Q. Since Q equals C times V, this becomes C times V plus C times V plus C times V. Factor out the common voltage we multiplied by open bracket C plus C plus C close bracket. So the total capacitance becomes C equivalent equals C plus C plus C. This is much simpler than the series case. In real circuits, parallel arrangements are used when we need to increase the overall charge storage, like in power backup circuits or decoupling systems. Look at the diagram. Every capacitor shares the same voltage but contributes its own charge.
Now it gets slightly more interesting. Mixed or series parallel combinations. Real-world circuits rarely use just one configuration. We often see a blend of series and parallel capacitors. To simplify such networks, we go step by step. For instance, imagine C1 and C2 in parallel and their combination in series with C3. First, we add the parallel ones. C parallel equals C1 plus C2. Then we use the series formula with C3. 1 over C equivalent equals 1 over C parallel plus 1 over C3. This stepwise reduction helps break down even the most complex networks. As shown in the diagram, it's crucial to recognize which parts are in series and which in parallel. This logic is at the heart of every circuit simplification technique used by engineers.
Capacitors aren't just about storing charge, they store energy, and how they're combined affects that too. The energy stored in any capacitor is given by U equals 1/2 times C times V squared. In a series combination, Since the total capacitance decreases and the voltage is divided, the overall energy stored is usually lower than in the individual capacitors. In a parallel combination, each capacitor stores energy independently since the voltage is the same for all and total energy is just the sum of each. This becomes super important when designing things like defibrillators, where you need a precise amount of energy delivered in a short burst. Miscalculating stored energy can make such a device ineffective or even dangerous. Always remember, the combination configuration can influence not just the capacitance, but also the energy behavior of the entire circuit. All right. Let's apply all of this in a real question. Say we have three capacitors. C is 4 microfarads, C is 6 microfarads, both in parallel. This combination is connected in series with C, which is 3 microfarads. The entire arrangement is connected to a 12-volt battery. Step 1. Compute the parallel part. C parallel equals 4 plus 6, which is 10 microfarads. Step 2. Use the series formula with C. C equivalent equals open bracket 10 times 3 close bracket divided by open bracket 10 plus 3 close bracket. That gives us 30 divided by 13, which is approximately 2.31 microfarads. Step 3. Calculate the energy stored. U equals 1/2 times 2.31 times 10 to the power negative 6 times 12 squared. That's U equals 0.5 times 2.31 microfarads times 144 volts squared, which comes out to roughly 1.66 times 10 to the power minus 4 joules.
Let's quickly revise what we've learned about capacitor combinations. We explored series combinations where capacitors share charge but divide voltage, giving us lesser total capacitance. Then came parallel combinations where each capacitor holds charge independently at the same voltage, leading to greater total capacitance. Mixed arrangements need careful simplification, but the rules stay the same. Apply series and parallel formulas step by step. And don't forget about energy. Depending on how you combine capacitors, you influence how much energy they can store, which is key in many electrical systems. I hope this session helped you understand how combining capacitors isn't just a textbook exercise. It's what makes real-world electronic circuits tick, from flash cameras to power backups and advanced medical tools. See you in the next concept video, where we unlock even more mysteries of electrostatics.